welcome to Particle Week. This week we're going to focus on particle physics, but in particular, I just want to focus on quantum mechanics revision because all other particles physics is quite easy. If you actually remember what is quarks, what is hadrons, and all those things, they are fine. But as a concept, quantum physics is more difficult than any other part of particle physics. That's why I am putting a highlighter on it, and we're going to go through it today. In particle physics, there are three different main branches of ideas that you need to understand. The first branch is photoelectric effect. The second one is excitation of atoms and electrons. The third one is how is electrons both a wave and a particle itself. So, firstly, main branches of idea. The first branch is photoelectric effect. Before we know what photoelectric effect is, we need to understand things. Firstly, what is EV? EV and joules can be inter-exchanged. How? We know that voltage is energy per charge. Okay, so when you talk about EV, this E, this one is a charge of an electron. Okay, so how do you turn EV into joules? If I rearrange this equation, energy is charge times volts. Okay, so when you say that I've got one EV, that means that I've got one charge of an electron, which is 1.9 times 10 to the power of something, I can't remember, you need to look at your formula sheet, times the volts is energy. If you have got one EV, that's one volt. Two EVs, that's 2 volts. 3 EV, that's 3 volts. This is how you turn it to how many joules that is. So in here, that would be joules. This is E, which is charge of electron, volts. This is a constant. This is not. So this is a proportion of that. So every single time you ask, they say, I'm giving you this EV, this amount of EV, that is joules. Okay? Joules can be changed by the EV, just very, very much like that. This is a little bit tricky because this equation is in the electricity formula, not quantum mechanics formula. So it's sometimes very, very difficult to remember. And if our teachers like you see online, most of the online videos, they give you a number, you memorize the number. I don't like that. This is not in the exam. Use this instead. Alright, second idea is an idea called E equals HF. What is that? This is the energy of a photon. When something is traveling in the speed of light, okay, another idea, which I'm not going to talk about today, but obviously Einstein's equation. So, if mass is traveling at the speed of light, that turns into energy. And in electromagnetic spectrum, energy are photons. Energy are packets of photons is packets of energy. And that energy turns into energy. Why? Because it's actually traveling at the speed of light. Remember, anything that's not traveling at the speed of light cannot be counted as energy. For example, this is a ball pen, right? This ball pen is not traveling at the speed of light. So this is no energy. But if I throw this hard enough, which I can't, this will turn into energy if it's traveling at the speed of light. This in turn explain to us why electrons is partly wave and partly particle, because some electrons are traveling very, very close to the speed of light. Anyway, let's talk about this. So energy on photon, E equals hf. Whenever you have got energy on a photon, whenever you have, so photons is from the EM wave spectrum. So EM wave spectrum has a wavelength, has a frequency. So this is talking about the wavelength and frequency. And we know that photons are energy, so this is, whenever you get the frequency of that, you can turn it to energy really straight away. So, as I said, photons and energy, these two ideas are completely interchangeable. Okay, so what is so impressive about this? What does everyone know? Everyone find it very, very difficult, very difficult to comprehend this. Let's do 4 situations together. Dim blue light, dim red light, and bright blue light. Oh, use black. And bright red light. So, when we are talking, well, these things, you can visualize it. What situation is it? Like just turn a blue light bulb higher and higher, something like that. But what are we talking about in terms of photons? How many particles in dim blue light? How many particles in white blue light? Dim blue light, for example, will have 3 photons. But bright blue light, for example, will have a higher number of photons. So, dim blue light and bright, dim and bright, this is actually an increased number of photons. Okay? So in wave, in the idea of a wave, this is increasing amplitude. Amplitude determines how bright something is. This is the increased number of photons. Take a minute to actually understand what it means. One more time. So, when you turn something brighter, when the light is not that bright, too brighter, you're increasing the amplitude. You're increasing the amplitude. Because, for example, each of these, this is not right because blue is not this region. Let's say this is 1 eV, let's say this is 2 eV, 2 eV. Each one blue light is 2 electron volts, or let's say 2 joules, or something like that. In total, this will be 6 joules, 6 eV, right? Okay, and here it will be 14 eV. All of these photons are the same energy, but there are more of them, so it's brighter. Okay, but what if we change color? We change color. Let's say all of these are reds, the same brightness. In here, dim blue light, dim red light. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You can see that in here, the same. You are increasing the number of photons and increasing the amplitude in here. But what changed between dim blue light and dim red light in here? Energy of each photon will decrease. What does that mean? That means that instead of 2 eV, it could be 1 eV, 1 eV, 1 eV. Do you see that? If I have at the same brightness, both of them has the same amount of photons. But because each photon is less energy, you get 1 eV times 3 instead, so it's 3 eV. So the total energy in here, it has decreased. Okay? If I have the same amount of energy, let's say this is not 7, this is 6. Actually, let's do this first. So if it's 6 photons in here, each photon is 1 eV, so in total there will be 6 eV. Okay? So you can see that bright red light in this situation has the same total energy as dim blue light, but the energy per photons is less. It's just brighter because it's got more. This is a very, very important concept before we understand the photoelectric effect. Okay, so we've got two situations here. We have got dim red light and red bright light. We've got blue dim light and blue bright light. We have got a circuit in here, and this is a very, very, very micro emitter that can measure very, very in very, very detail how much current or how many electrons is through the circuit, and we have got a zinc plate. In dim light with red and blue, which one is going to get the electrons moving? Yes, the blue dim light is going to get the electron moving. Dim red light is not going to get the electron moving. What if we turn the brightness up? Blue will still get the electron going, but no matter how bright you turn the red light, the electron will still not keep moving. Why? Because we have got a concept called work function. Work function is the energy needed to get the electron out of the atom. It's not just that, it's the minimum energy needed to get the electron out of the atom. So imagine you've got atom, you've got electrons around it. In order to free the electron, you need to give them a minimum amount of energy. That is called the work function. So, so you can practically shine an electromagnetic wave onto a piece of metal, and actually, electrons will just come out. That is called photoelectric effect. Photoelectric effect means photon giving us electrons. So, 3 ideas. Number 1, energy and photons are the same thing, linked by H. So, joules and hertz, or joules and lambda wavelength is linked. Number 2, joules and EV. Whenever you see EV, that is joules as well. The 2 is linked. Joules can be coming from kinetic energy. Same thing. Joules and EV are exactly the same thing. And also, photoelectric effect is photons releasing electrons, but only, and electrons can also release photons a little bit later as well. We'll talk about it a little bit later. But it's total energy of 1 photon equals the minimum energy needed to get the electron out of the atom plus excess energy. What is this excess energy? In this side is photon, in this side is electron. Obviously, this excess energy is going to turn into kinetic energy of the electron. Okay? Total energy of 1 photon. What do we know about red and blue light? In here, when you turn dim to bright, this is increasing the number of photons. But when you turn red into blue, you're not actually increasing the number of photons. You're increasing the energy of each photon. That's why the photon, each of the energy from each photon, look at this total energy of 1 photon. So if you actually increase dim to that bright, you're increasing total amount of photon. You're not increasing the energy of each photon. Total energy of each photon can only be increased by increasing the frequency of photon. Look, E equals HF, right? The only way you can increase the energy of each photon is increase the F, which that means that gamma photons have the highest amount of energy. Why? Because gamma photons has the highest amount of frequency, whereas radio photons have the lowest amount of frequency. Why? Amount of energy, because lowest amount of frequency here. Okay? Let's take it a little bit. We'll do 1 or 2 questions about it. Don't worry about it, but we'll get there. So minimum energy to get the electron out of the atom, and sometimes because this is equal to that, we call this, this is caused by total energy of electron, and this is all excess energy. What if there's no excess energy? Well, there's no excess energy, that means that the energy needed for this has just the photon has just to release an electron. And this is a special case, because in this special case, that will be equal to HF. Okay? And this F is called threshold frequency. It's the minimum amount, a minimum frequency needed to release electron. Any higher than that, remember, HF and higher F, high energy. Okay? Lower F, lower energy. So when you have minimum amount of energy just about to release, that means that kinetic energy is 0. It's really, really difficult to envision kinetic energy being 0 because it's not moving, but it's just moving. So in this situation, threshold frequency is the minimum frequency needed to release electron. Obviously, we have got V goes at lambda, and in this situation, V is the speed of light because it's not energy if it's not moving at the speed of light. But this can be lambda as well. F will be lambda over V instead. So, or lambda of C. C is the speed of light. So you need to take care of that as well. But that's the gist of it. We're going to go through some questions in here, and hopefully afterwards you'll understand much more from this. Hi, welcome back. So question 1. A beam of light wavelength lambda is incident on a clean metal surface. So they are saying that the wavelength of light is halved, but the energy incident per second is kept the same. What is energy? Remember, energy is photon. When you say energy incident per second, that means that it is photons per second. One photon release 1 electron. That's why number of photoelectrons emitted per second will decrease. If you decrease energy per second, you decrease photon per second, and you decrease the number of electrons that's available. Alright, the second one is maximum kinetic energy of the emitted photoelectrons. When you have halved wavelength, you decrease wavelength, you increase the E. What is E? E is energy per photon. So if the energy per photon is decreased, remember our equation? Our equation is energy per photon work function plus KE. So if this is decreased, this is not changing, this will decrease as well. Remember, this does not equal to this straight away. Some of this has to be spent getting it out of the nucleus, not nucleus, electron shells instead. First. All right, so that's question 1. So question 1 is C. Question 2, in experiment, blah 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 blah. A charged plate illuminated from light emitting sources. The plate loses its charge when an ultraviolet light source is used, but not when a red light source is used. So this is exactly what we were talking about earlier with red and violet light or blue light. So let's look at number 1 first. The intensity of the red light is too low. Intensity, what does intensity mean? Write it down. Intensity is number of photons available. What determines whether something can be an electron is released or not? What determines whether a photon can turn into electron? This side is photon, this side is electron. This is light, this is electron. What determines it is that it overcomes the work function. What determines what overcome the work function is the energy per photon. Just increasing the brightness increases the number of photons. It does not actually increase the energy per photon. I'll say one more time. When you increase brightness, you increase then how many photons are there? But you're not actually increasing how much joules, how much EV is in one photon. That means that if you increase the intensity of a photon, it's not going to help with the work function, with overcoming work function. So A is not incorrect. No, A is not correct. B, E equals HF and E equals HC over lambda. B, it says that wavelength of the red light is too short. Actually, shorter wavelength is actually giving highest energy. So this is incorrect. The wavelength of a red light is too high. Higher wavelength means lower energy. Higher wavelength means lower energy. Okay? C, the wave frequency of the red light is too high. Incorrect. The frequency of red light is too low. Because lower frequency is lower energy. We gave us the last one. The energy of the red light photons is too small. Yes, correct. We need higher energy photon to overcome the work function instead. So 2 is D. Question 3. These type of graphs is very, whenever you see these type of graphs, you have to think, oh my goodness, that is a y-intercept, that's x-intercept. What are we talking about? If I turn this into, so our equation will be energy equals work function plus KE, which is a KE, let's say that. Yep. Why are they doing why are they doing x-axis? Why are they doing y-axis? So E, where does E come from? This comes from HF. Okay? I'm going to rearrange the equation. Equals KE. Why are they doing x-axis? Why are they doing y-axis? They're doing y-axis and maximum kinetic energy. Oh, no, incorrect. Yep, that is going y-axis. And then x-axis is frequency of the incident photons, is x-axis. So very easily, we can see that you can actually look at this instead, y equals mx plus c. So F is x, KE is y, so the slope in here, or the gradient in here, will be what h is, and negative, the y-intercept will be the work function. So which graph shows the result of a metal X giving a higher function than metal Y? So you can see that C and D is 100% not correct, because C and D implicates that C and D, the y-axis for Y is 0. that indicates that you don't actually need any work function, and you don't actually need energy to release an electron. That's 100% incorrect. If you extend x and y in A into the y-axis, you can see that in x, the y-intercept is lower than y, than B. So, question 3, the answer is A, because at A, x, the y-intercept is lower than y. So y has a higher work function than x because it's negative y-intercept. Right. It's A, x and y. X is here, y is here. Okay, if I extend that, this is more negative than this, right? Yeah, but C corresponds to negative work function. So that means that y has a higher work function and x has a less work function. Okay? All right, question 4. Question 4 is the one tricky one that I really want to do with you. So what I want you to do is try question 4 first. I'll give you a hint. You need to turn joules into EV. How? One EV is times 1.6 times 10 to the power 19, which is E, will be equal to joules. Turn it back to go back to joules. And also, what is E equals work function plus KE? E is H times F. But that equation, that question did not give you F. What did it give you? It gives you lambda, so you need to use E equals HC of lambda instead. Okay? Try. Okay, we have a try. Great. So firstly, let's look at our information first. Total energy of one photon is 4.1 eV, and no, work function is 4.1 eV, so I can actually put 4.1 eV in here, but you can do this in terms of eV. I don't want to do it in terms of eV because let's do it in terms of joules instead. You can do it in terms of eV. That's actually a hint, it's a big hint of you doing it in terms of eV, but kinetic energy is eV, so all of these you can do it in terms of eV, but I'm going to do it in terms of joules instead, because that's what I want. Alright, so let's look at this first. You've got E is energy of one photon, and energy of one photon, how do you calculate that? Is H times F, or can we do this instead? No, because they didn't give you F. What did they give you? They give you wavelength. So it's HC over lambda instead. So that is going to give you 6.63 times 10 to the minus 34, which is H. C is 3 times 10 to the 8. Lambda, which is in the question, is 290 times 10 to the power of 9. This is going to give us 6.8586 times 10 to the power of minus 19 joules. So that is the joules of one photon. I'm also going to put this work function, it's 4.1 eV. I will need to, because I want to do the entire thing in joules, I want to turn it into joules instead. How do you turn this into joule? Yeah, we know that 1 eV is can be turned into joules. How? I times it by the charge of an electron, which is 1.6 times 10 to the power of 19. This is going to give us 6.5689 times 10 to the power of minus 19. I'm not going to lie to you, I have trouble doing this question as well. A benchmark of you being able to do this question is this should always be bigger than this. Why? Because if the energy of one photon is less than a work function, this thing is not going to move. Okay? Is this bigger than this? Yes, 6.85 is bigger than 6.56. Same order of magnitude. So I have got some excess energy. What is excess energy? The excess energy is kinetic energy. So kinetic energy will be equal to 6.8586 times 10 to the power of 19 minus 6.5689 times 10 to the power of 19. So this is going to give us 0.2897 times 10 to the power of 19. So the question is asking you to go back to EV. So in order for us to go back to EV, I need to divide 1.6 times 10 to the power of 19 instead. So this is going to give us 0.186 EV, which is 0.19 EV, which is answer A instead. Okay, so using these ideas that I just talked about in the multiple choices, please, could you please try question 5 and question 6. Question 6, the end of question 6 is talking about de Broglie's wavelength. If you don't know what that is, you can wait until a little bit later to complete this question, complete the last one of the question. Do the rest of that first. So that's that. I will come back and do the second part, excitation, and also question 11 as well, because question 11 is just turning EV into joules and etc. etc. Okay. I'm going to come back to do excitation, DA excitation, and energy levels. Okay, so welcome back to excitation and de-excitation energy level. From this point on, that is much easier. Remember, the most important thing about this is that whenever you see EV, it is energy. Whenever you see energy, that is EV. The same thing. Okay? So you've got different energy levels. And all these energy levels actually are negative. Why? Because it's convention. What is convention? We model storing energy as a negative energy. We model release of energy as a positive energy. So whenever you store something, we explain it as negative energy. This is exactly the same as gravitational potential energy, or when you store energy in elastic bands. Technically, if we using engineering and physics convention is negative energy. But anyway, what you need to know for the exam is that when you are at zero energy level, when zero EV, the electron is free. And you need to absorb energy to become free. So that's why the energy levels are negative. So what is going on in this energy level thing? When you excite the electron, how can you jump energy level from small to higher? You receive energy. And how do you receive energy? What is energy? Energy is from photons. So you actually absorb photon. You absorb a bit of light. Okay? So what happens after a while? After a while, it actually drops because there's nothing holding in this energy level anymore. So it actually drops. When it drops, it release energy. When I say drop, I mean de-excite. So release energy. What is energy? Energy is photon. So it actually releases a photon instead. And what photon it releases depends on what frequency it is. How do I know the frequency? We know E equals hf. The range of energy will correspond to range of frequency. Obviously, the highest frequency will be gamma rays and X-rays. Lowest frequency will be radio waves. So that is very easy. That the concept, if you totally understand what I'm talking about in here, it's not a difficult concept. One more time. It jumps up. Why? Because it's receiving energy. In what form? A photon. It falls down, de-excite. Why does it de-excite? Because you wait. Like, it can't stay in the excited state for long. When you excite, you need to supply it with energy. When it actually de-excites, anything can de-excite. Like, this is the normal state, okay? This is where the nucleus is positive, right? It's pulling the electrons in here, okay? Unless it's free of this nucleus, unless it's really far away, it would put it back down because the nucleus is here, okay? When it de-excites, when it goes back to different energy level, lower energy level, it actually releases energy. What energy is this? This is a photon. Very, very easy. So what I really want you to do is we're going to do question 8 together, but question 9, you need to examine it. So there are questions about excitation and de-excitation. The most important part of this exercise is that you make some notes and do some memorize the answer so that you can actually regurgitate the answer when they ask you the same thing. Question 8. An atom, fluorescent tube, absorb a photon of ultraviolet radiation. It causes excitation of the atom from its ground state, and then afterwards a photon is then emitted. Why is a photon emitted? The photon is emitted because the electron de-excites. So firstly, let's look at what is B and what is C. In B, you can see that excitation is in 2 stages. When you see the excitation is 2 stages, that means that it has received 2 photons, which is incorrect because there's only 1 photon of ultraviolet radiation. C is also incorrect because it's received 4 photons. Okay, compare A to D. Which one is more correct? A is incorrect because it says that it receives ultraviolet radiation where a photon of visible light is received. Which one has more energy? Ultraviolet. Why? Because it's higher frequency than visible light. That's why when you have the excitation will be higher than the excitation. So that gives us the answer of D instead. Alright, question 9 and question 10. Question 9, it says that how the collision of charged particles with the gas atom causes the atom to emit photons, and how spectral lines are explained by the concept of discrete energy levels. What I don't want, please read the marking scheme. And these 2 questions are actually sample questions. That's why I gave you these 2 questions. These are question 9 and question 10. And question 10 is talking about a fluorescent tube and how a mercury atom become excited and how it emits photons. And also, why does ultraviolet photons emit to visible light? These are all in the syllabus, and these are all very some questions. So, what am I trying to say to you? Number 1, what is this line spectrum? A line spectrum is a diffracted spectrum of light. Each line represents 1 wavelength. So, why do they have discrete means certain? Just one, like not a spread, just 1 wavelength. Why is there a discrete energy level? Because it is a specific wavelength. Each wavelength represents a fall. For example, if I fall from here to here, this is going to release 1 photon. If I fall from here to here, it's going to release another photon. Which one has high energy? Think about it. The drop is higher, the photon energy is higher. If the photon is energy higher, E equals HF, higher E will have high F. Okay? In this version, E equals hf, we have got lower energy, so we have got lower F. So if these are all invisible by spectrum, this is going to give us violet, whereas this is going to give us red, for example, because violet has higher frequency than red. That's why you have got different frequencies in the spectra. So have a look at that. Have a look at these two, and please to memorize these phrases. So you have got arsenal of how to answer these type of questions. Okay, right. Do question 7, 8, 9, 10, 11, and 12. And especially question 12, because question 12 will have a lot of questions that is related to the last two questions. Okay? If you do not understand this, please comment on below, and I'll snip down textbook pages for you again to have another detailed look on this. But the concept of this is not really not that difficult. Okay, spectral line means that this is the different photons, and each jump is a discrete energy, discrete specific energy. So each specific energy is going to give us a specific frequency. Okay, try these questions first, and then I'll come back to that if you have any problems. But you need to email me. Okay. All right. Okay, welcome to the last part of our particle version. It's a long video, but we got that to the end. Last part is wave versus particles. How a photon can be, or photon or any particles can be a photon, can be a wave, and electron and a particle at the same time. There are questions, most of these questions about electrons, but photons can also travel at the speed of light. So sometimes photons can have wavelength as well. It's called de Broglie's wavelength, because de Broglie is a person who actually put an electron into a plate of graphite, and you see these rings. The reason why we have rings is because of the slits of the graphite basically behave as a diffraction grating, because the slits is very similar to the wavelength of the electron, and they interfere and diffract. Point number 1. Diffraction and superposition. These are all wave properties. Okay, point number 2, photoelectric effect. This is a particle or photon property. Do you understand this? So, as the wave up together, the amplitude and the displacement will increase or decrease, and diffraction, one wave turning into a circular wave, or recover after encountering something that's in its way, that is a wave property. But saying that one photon releases one electron, the idea of one particle or photon release one particle electron, this is the particle property. So these two are the concepts of what are wave and particle. Sometimes how can a particle move at the speed of light and turn into wave? And this is the concept, what we're talking about. And this equation is coming along, lambda equals h over mv. If something, a speed of a particle is here, the mass of m is the mass of a particle, usually an electron, and h is Planck constant, which is 6.63 times 10 to the power 34. Anything that's approaching the speed of light, its particles light enough, then you might express it in terms of a wavelength of a particle. Obviously, if you have wavelength of a particle, you have frequency of particle. Yeah. Anyway, so let's look at question 13. Actually, I'm not going to do question 13. But if you look at this, you can do question 13 yourself. You can, question 14, you can also do yourself. What I want us to do together is question 16. Question 16. Electrons are moving in a beam the same de Broglie wavelength as photons in a separate beam, moving at a speed of 2.8 times 10 to the 4 meters per second. What is the speed of electron? So they're asking you have electrons and photons. They all have the same wavelength. So what is the speed of particle if you have an electron? Okay, so let's rearrange the equation. So whenever you do questions like this means that it's a ratio question because you change something and kept something the same. Let's identify what did they change, what did they not change. Lambda equals h over mv. Did they change lambda? No, they didn't change lambda because it says that it's the same wavelength. Did they change h? No, they didn't change h. Why didn't they change h? Because it's constant. Did they change m? Yes, they did. Because mass of the proton and mass of the electron is different. So hence, if they change m, they change v as well. So let's rearrange the equation. mv equals h over lambda. So we know that these two things are not changed. This, I can say that this is a constant. So our equation will be m1 v1 equals m2 v2. Wait a minute, what is this? It's actually momentum. This is actually exactly what we're talking about, but this is what really exciting. I didn't realize that until I'm doing this right now. Anyway, we're not talking about this, talk about this first. So what is the mass of electron? Mass of electron is actually 9.11 times 10 to the power minus 31. And then this is, so this is electron, this side is proton. So we are finding the speed of electron, so I'll put the V in here. Proton is 1.67 times 10 to the power of 27 minus 27 times the velocity of proton, which is in the equation, which question is 2.8 times 10 to the power 4. So you will get the answer as D. V will be 5.1 times 10 to the 7 meters per second. Right, so this actually concludes the entire video. Please do question 14 to 17 as well after this video, and hopefully you understand a little bit more about quantum physics. And as usual, please save your questions so that we can deal with it when I see you or when Mr. Gorman see you. And yeah, twice.